Okay, so hi, my name is Ian and I'm the president of Mega. Welcome to Mega Hackathon's 2026 first guest speaker presentation. Today we have Akriti, Ishan, and Krishna who will be doing a presentation on breaking the silos, building interpretable multi-agent systems with A2A and MCP. Feel free to begin when you're ready.
Can I share my screen?
Sure. Let me see. Is it allowing you or?
Mhm.
Okay.
Oh, yeah. First of all, I want to thank Mega Hack. It's an honor to be on the stage with people who are actually building the future. Last few years, we have spent talking to AI. We've all built wrappers and played with prompts, but today we want to talk about the next steps. We want to talk about how we stop building isolated chatbots and start building distributed systems. So today is how we give AI hands to touch our data and voice to talk to other agents. So let's dive into building interoperable multi-agent systems. So a brief intro about us. I'm Akriti. I have Krishna and Nishan with us. We are engineers from Meta, Google, and Netflix. I work for Meta Messenger team. Previously, I worked with projects related to AI-assisted development and developer productivity tools. So yeah, let's talk about the AI silo problem. Imagine you are assigned the most important group project of the semester. Your teammates are three smartest students on the group. Your student A, let's say, is OpenAI, is genius in planning and strategy, but there's a catch. They only speak French. You have a student B who only speaks Japanese but is the best coder in the department. You have student C, which is a master researcher, has read every book in the library but only speaks German. So on paper, it's a dream team, but in reality, it's a nightmare because they are all sitting in soundproof glass boxes. They can each see each other through the glass. They can see that student C has the data, but they can see student B is ready to code, but they cannot share notes. They cannot even pass the USB drive, and worst of all, they cannot even agree on who should start first. And this is AI silo. Today we have genius models from different companies, but they are trapped all in their own ecosystems. They don't share a language and they don't share a toolbox. And yeah, as a result, you, the user, have to be the translator. So today we are going to talk about how to break this glass. So there are three walls of the silo, like the issues with the silo. One is the data wall. So let's say student A has keys to Google Drive and student B has keys to your local file system, but in reality, they cannot see the same data, same evidence. The language wall. The language wall is like let's say we have GPT and Claude. They both want the inputs in a different way. Like Claude wants XML and GPT wants JSON. And the third is the context wall. I think this is the most frustrating one. Every time you walk away from the glass box to grab a coffee, everyone's memory is wiped out. And the conflict you come back, you have to re-explain the entire project from page one. So why is silo a big problem? So silo is actually a business killer. Up until now, we have talked about frustration of silos, but in reality, it becomes a huge problem with the companies. It reduces engineering velocity because right now, if you connect to OpenAI to your SQL database and then want to move to cloud, you have to write the custom code bridge again. The switching cost is high because every time you try to change to a model, let's say there's a new model which is cheaper and faster, you have to rewrite everything. And the system fragility. In a siloed architecture, you have a single point of failure. Let's say one API is failing, there's an outage, and then you're kind of stuck. Fourth is a limited agent synergy. This is the biggest tragedy. We have a specialist models that are world class at maths and at coding or creative writing, but if they cannot talk, and we can't compound their strengths. So if we are somehow able to make these agents talk, we can get the best out of everyone, and it's a win-win. So let's talk about MCP. So how do we break this glass? So how do we let the French speaking genius share their notes with Japanese speaking coder? Why don't we try to teach all of them the same language? We can do that, but it is risky, right? What if they don't learn that in time? So instead, we use a universal plug. In simple terms, MCP is an open standard interface. It was developed by Anthropic, but it's built for everyone. It decouples the reasoning engine from the data provider. It acts as a hardware abstraction layer. Think of it as USB C for the world of artificial intelligence. To understand how this works, think of it as a biological system. The brain, it's the AI model, which is like either ChatGPT, Claude, or Llama. The world is where your actual data lives, your Google Drive, your company Slack messages, or your file system. And the nervous system is MCP. And this is the breakthrough. MCP is the standardized wiring. It's a set of nerves that let any brain plug into any part of the world. Because of MCP, the brain doesn't need to know like how Google Drive works. It just needs to know how to talk to it. So before MCP, if you wanted a new brain to see your world, you have to rewire the whole house. But now you just have to plug it in, and if a better model comes out, you just unplug the old brain, snap the new one into the nervous system, and your data stays put. Uh, so now that we know that MCP is a nervous system, it has three distinct layers. So one is the host. It's the home of the AI, the place where the conversation actually happens. Like it could be the chat app like Claude AI, or it could be the IDE like Cursor or VS Code. Next is your client. It is the most important piece as a developer. So the client is the translator. It's a specific part of software that speaks the MCP language. Finally, we have the server. It is the toolbox that holds the actual data. It is your Google Drive, your Slack workspace, or even your local file system. So, to understand why we really need a new standard, let's look at the old way. So, this is a glue code. So, if you look at it, it's a trap. It seems simple. It's just like it, but it's hard coded custom logic for OpenAI function calling schema. So, and in future, if you want to move to Claude, you have to change it to XML format. Looks simple, but if you think about like changing 50 such layers, then it can be a problem. So this is how your server code looks like. This is your toolbox with like MCP integration. We can notice how clean the code is. We define a tool called read document. We give it a description so AI knows what exactly it's for and how we define the input it needs. A simple path string. This code does not mention OpenAI or Cloud or Llama. You write this logic once and it sits on your server like a universal light socket. And if you look at the client side, which is the brain, it's very simple. When the AI wants to use that tool, it sends this exact JSON packet with the method. It doesn't matter if your brain is GPT or any other local model running on your laptop. The brain just says, I am calling read document for this specific files. The client translates that and the server executes it and the data flows. Uh, yeah. So now we have solved the data problem with MCP, but our genius students still cannot talk to each other. They cannot they can't reach to the someone in the same toolbox, but they are still in their glass wall. So they still don't know how to work together. They still work as individuals, and this is where your agent to agent or A2A comes in. So technically, agent A2A is a high level coordination protocol. It's a set of rules that standardizes how different AI systems delegate tasks, share current state, and negotiate. So think of A2A as the professional etiquette of AI world. In a human office, we have etiquettes. We just don't scream, hey, do this work. We send calendar invites, we attach a brief, and we ask for a deadline. And A2A is like that brief for robots. Without A2A, a GPT-4 agent is just like shouting in the void. It might generate a brilliant plan, but it has no way to hand that plan to another model. If you want GPT to talk to Claude, you, the human, have to manually copy the text. The agents are blind to each other's existence. But with A2A, the glass boxes vanish. Now, a GPT-4 manager can see that task requires deep coding and intensive research. It doesn't try to do it all. Instead, it sends a formal A2A request to Claude Coder and a Llama researcher. It says, Claude, here is the objective, Llama, here is the context. Report back to me when you're done. And this is how we move from chatbot to an autonomous organization. So, yeah, so when you see two agents talking, it's easy to think like they are just chatting like humans in a WhatsApp group, but that's a mistake. If they send just plain text, that can be disorganized as a group of students trying to pick a restaurant. A2A is different. In normal chat, you send a string of words. In A2A, agents send structured packets. These are precisely formatted bundles of data that act as legal contract for a task. A typical A2A handshake contains three layers. The capability request. So manager doesn't ask like who can help. It just sends a requirement that, hey, I need help with Python data wizard visualization. Can you help me? The next is the context pass. It says, hey, I already ran some analysis. Here are what I already found. Just like work with this. The third is cost negotiation. When the manager would also say that, hey, I'm authorized to only pay 500 tokens for this task. Do you accept? And the specialized agent checks its own burn rate and either accepts the job or negotiates. So this is digital economy happening in milliseconds. So why do we bother with all this formatting? So in text, a researcher might get confused, but in A2A, the capability ID ensures that the right brain is on the job. So let's dive a little bit deep into how the protocol looks like, an ACP protocol. So if you look at the method at the top, it says like agent and delegate task. And this is just a standardized JSON RPC call. Both agents speak the A2A protocol. The worker knows exactly what this means before it even reads the rest. It is like passing the baton in a relay race. Next is our objective. Instead of rambling a paragraph, we provide a concise mission. Hey, generate a heat map from the CSV data. We're giving agent what does the state of done mean. Third is context ref. It's the most important line in the entire presentation. Look at context ref. So it here points to MCP local files and data sample.csv. This is exactly where A2A meets MCP. The manager isn't sending the whole 50 MB file over the internet. It's just handing over a pointer. It's giving worker the keys to the local toolbox. The worker uses its own MCP client to reach out and grab exactly what it needs. And finally, we have deadline, which is 5,000 milliseconds. So if a worker can't finish in 5 seconds, the manager kills the task and tries a different specialist. So it's actually pretty amazing. So this is how you build reliable systems and kind of not fall into deadlocks. So if you've been following along, you might be spinning with like JSON packets and server definitions. So let's strip that away and look at the logic for some time. A2A is all about coordination and delegation. It's a social layer. It handles who is doing what and how much it costs and when it's due. A2A is the manager, and the manager doesn't get their hands dirty with the database. Manager just gives the orders, sets the strategy, and makes sure that the team is on track. So, and if you look at MCP, MCP is just the execution layer. It's the physical layer. It handles how do we read the data, how do we query the SQL, and how do we post to Slack. So it's specialists with equipment. So we talked a lot about MCP and A2A. So we have the protocol, we have the teamwork, but how do we actually give an agent its professional degree? And how do we make sure it doesn't break the rules? So we use skills and hooks. So a skill is like a modular bundle of prompts and MCP tools. Think of it as software package for an agent's brain. In past, we tried to give one agent like 100 different tools. This caused like model confusion. The AI would get overwhelmed and try to use a hammer to fix a light bulb. So the solution here is like you don't give a plumber a stethoscope. You just give them plumbing skills, which contains like in this case maybe for plumber a wrench tool, and like how to fix the pipes logic. So and kind of common skill that we have in industries, like data analyst skill. Uh, so any agent in your A2A network can equip that skill the second they need it. It's on demand expertise. So if skills are what an agent can do, hooks are the sensors that control when it does them. Hooks are code level triggers that intercept the conversation to make decisions. Pre-task hooks. Before you answer the user, use MCP to check if database is even offline. So it's a safety check. Post-task hook is like, let's say, after you generate the code, use A2A to send a message request to tester agent. It's automatic handoff. Uh, yeah. So here's an example of like how a simplified agent hook in TypeScript looks like. So we have talked about theory a lot. So let's dive into this. So if you look at the top of the code, we are not just creating a generic AI. we are creating a coding agent which is called Cloud Coder. So in the skills array, we are passing Python data visualization skill. So it's like a bundle here, pre-packaged bundle containing specific tools and rules that turn a general AI into professional data scientist. So instead of coding the same visualization logic over and over, you define this skill once. So next we look at our first hook, which is on task received. So this is a pre-task sensor. Before the agent even thinks about user request, this code triggers. It checks, is the MCP server online? Do I have access to the file? If the answer is no, the agent stops before it makes any mistakes. And this is kind of how we eliminate AI hallucinations. So next is on task complete. This is post task sensor. Once the code is generated, the agent doesn't sit there waiting for you to copy paste. It automatically triggers an A2A handshake. It packages the results and sends it back to the manager agent. The baton is passed effortlessly. The human never touch a single line copy paste button. So without hooks, agent is just a talker. With hooks, agent is a professional who knows exactly what to execute and exactly when to call for a backup. I think I'm now gonna pass to Ishan. Do you want to, Ishan, give a brief about yourself?
Yeah, thanks, Akriti. I'm Ishan. So I'm a research scientist at Netflix, but prior to that, my experience was mostly in self-driving space. I will walk you through like a full-fledged like demo of a long-running agent for a specific application, which I feel is very useful in like general like space also. So let me try to present my screen. Okay. Okay. So I think today I will talk about how can we basically like whatever we learned till now about like different components like hooks, skills, MCPs, etc. Like how can we implement using that like a Figma to code agent? Like basically we want to I'll basically go through like what are the different problems here. Like basically like what is Figma, like why it is a problem, like why we want to solve it, and also like what's a practical way to solve it like through some multi-agent system design. And I'll also walk you through like some real inputs which are exactly available in the Figma community and how I use that to kind of like create like a output which can be used easily. Like it's the output which is the agent generated here. Okay, let me go to the next slide. So yeah, just a brief primer about Figma. So Figma is like a tool I think which is used a lot by the design community to basically like showcase whatever your design vision is and communicate through that with the software developers and engineers. And basically the engineers then use that Figma design, whatever the designers created, to basically like make an app which is used as a mobile app or a web app in the internet space. So Figma files essentially they are like structured pages. Like so I'll show you like a visual in the next slide, but like essentially like it's like a structured design data. So it's not just like an image. So you basically have like some kind of like hierarchy in the signal here. Like you have like pages. Within each pages you have like multiple of layers, and each layer has like frames, and then within the frames also you have like components which you can share. And all the intent of the designer like lives in these components, styles, like font, etc. Like and what kind of hierarchy they want to use to make a web page. And and to really like translate this whole Figma file into like a good code, like you need basically like to understand that in structure and not just in like just images, pixels, etc. And the output of this is not just like it's like a multi-screen behavior. Like basically like each endpoint in the app, like when you use the web app, each endpoint goes to like transition into like another app. So you need to also understand the transitions perfectly when you basically like build it. So it's a very complex task for the agent. Like it's not like a simple task where you ask a question and you get output. It needs like multiple thinking steps involved here. So I feel like it's a very complicated problem which currently to humans like it takes like weeks to months sometimes to build this thing. So it's like a very practical example to give here. Okay, so here's like one example, like some snapshot of like a Figma file, like how the Figma interface looks like the designers, the way they use it. So basically, like on the left, you see like these pages, like the designer here created like 4 pages, like design, style, etc., etc. And then you have like for each page, you have like layers. So there's a layer hierarchy there. And then like for the agent, this is like very crucial to like, because like as I said before, like Figma is like a structured data, and like how it can use it to kind of like understand the full layout and transitions, etc. So for example, this is like a Figma design of a car rental website, where like the designer is trying to put his like different like pages, like how the different pages in the car rental app should look like. Okay. So and why Figma to code is like a painful thing also. Like I think like as I mentioned before, like why we want to solve it is very important to know to kind of like get the full like idea and about it. Like so it's very different. Currently it's used a lot in like a lot of enterprises. Like each enterprise have their design team and have their like software or front end team, back end teams. So it's a very complex ecosystem where you need like a lot of cross team handoffs. Like basically the design vision needs to be translated to the software developers, etc. And also like the coding outputs, like the code output is not just like a single platform. Like right now there are very like a lot of low code tools like Webflow, etc., which I think are also used by enterprises. So to really make this application, you need to think about like multiple angles, like multiple delivery targets like React, Vue, etc., and like Webflow, etc. And sometimes the design must map to like the different front end and back end constraints, like and like workflow must be target aware and not framework assumed. Like so it's a very cross team and cross stack translation effort, and like there's a lot of like coding which is happening here under constraints. Okay. So I hope this is visible and like people can read it. But this is like I'll go through like a general like framework of like how we can make like a multi-agent system design for this design to code or Figma to code workflow. Uh, so this workflow basically like moves to like a design understanding. Like so basically like as every human being, like as I think as a human also, when we try to solve this task, we will first reason about it, we'll first think about it, we'll first plan about it, like how can we break this very big problem into small chunks and tackle it step by step, right? And also like at the same time you also want to have a capability where if you make mistakes, you have the capability to go back and correct it. Like these are the tools as a human psychology, like you use these kind of like notions to kind of like tackle a big problem. So it has to be closed loop. You can't like just assume that like you give input and you get output which is always correct. Like so you need to have this like closed loop ecosystem here. So for example, like in this case, like I'm showing like you get like you have this agent which we are building where the design input is like a Figma file and a task, and then like there is an orchestra agent which is like we can call it as a main agent, or there are different terminologies being used, but the job of this agent is to like have some vision about what is happening around it in some way. And then there are different like components here, like how do you read the design. Like we'll look in the next slides like how can we have the capability for the agent to read the design files, and how can it plan across different pages and different components, like how it can generate front end code. And then once it is doing that, like how it can like understand like what it has done, how it can understand whether it is right or wrong, and then go back and do it again if needed. So I think this is like a very I would say like a very closed loop ecosystem, which I think is very, I would say like it's translated to like a lot of different applications, not just this Figma to code, but this general philosophy can be applied in different domains also. And then I think like there needs to be a concept of shared state, like which can be used both by humans and the agents. Like this shared state can be used for like keeping track of like plan, like progress and different checkpoints. And like you can also use it for further evaluation. Like if you want to, let's say, evaluate different agents, you can also use this shared state concept to understand the things. Okay. Okay, so I think like the very first step for building this, so I'm showing you like some abstract code screenshots. uh, Essentially like in this screenshot, I think like what we're trying to do is like we are trying to create like an agent runner. Like so the basic definition of an agent runner is like you tell it like, okay, this is the workspace. So workspace can be some kind of like file system in the cloud container or in your local machine, which you need to point it to, like, okay, you have to only work in this workspace. And then there are this concepts of like system prompt and the user prompt that tells the agent like, okay, what is the goal, what is the task, just to give it a feel of like a role play. And then if you see in the top, I have mentioned like some allowed tools. So these tools are like essentially like as we were mentioning in the previous slides, like MCP tools, or any kind of like local tools which you have created. You can subscribe to that to the agent. And then I think like there are like other things like also going on here. Like for example, like there if it's MCP tool, you also need to make like a corresponding server. Like you need to tell the agent like how to. You need to also start the servers so that the agent can use those MCP tools, because the agent will connect to the server and then use the tool. So you need to also do that process before you start the agent. And then like there are like some other things which I think we'll discuss about like in the future slides, like skills, hooks, how do you hook them up also with the agent. But the core philosophy is you need to have this agent runner, which you can like now invoke that asynchronously or synchronously and capture the traces. Okay, next slide. Okay, so I think so in this one, I think we're going through like a simple, like I think as I mentioned before, for this task, one of the very important point is for the agent to know like what it is building, like to have some understanding of like the Figma file, right? So in this case, like this is one example of how do you make a MCP tool. Now you can always make like a local MCP tool or like a server, like a remote MCP tool. But this, let's say, is example of like a local MCP tool, but you still need to mention these endpoints. So for example, in this case, we're trying to basically create like a bridge between design data and the agent. So in this case, you can see like you have like this philosophy of like using like authenticated way if you have this token for your Figma file, because you can't access anyone's Figma files, right? So you need to have like some authentication around that. But with that authentication, you can like use like Figma file APIs. So for example, in this case, you can see like this design request is basically like sending like a request to get the corresponding information for that file. And as I mentioned before, this file is also very big, like it's not a very small file. So there's a layering concept here. So basically like Figma file APIs provide you this like interface by which you can control how much you want to read. So in this case, for example, like I have this parameter which I specified called as depth, so which you can use to control like how much in deep you want to go to read that file. And so this is like a very important kind of a concept, because you want to give the agent the capability to read in like structured manner. And also like you can't just download the entire file, because otherwise you will just dump it into the agent's context, which might blow it away. In this case, like you basically show like there are two tools, like one is this get file and get node tree, which basically like we are trying to build here for this MCP server. And so similarly, you can build the same thing for other tools which you want to build. I guess like the interface remains the same. Okay, next slide. And the other concept is skills, which I think we discussed before. So skills are nice in the sense, and they're very now adopted. Like it's a standard now, which it is adopted by OpenAI, Anthropic, and Gemini. Like if you open the harnesses, you can. There's a standard way to use the skills now. The nice thing about skills is like how they're different from prompts. Like if you see like this is like some kind of text, right, which I've written here, like it's a markdown format. But the nice thing about like skills is that like the agent has capability to load them only when it is needed. So you don't in the case of MCP tools, the context of the tools you always need to load into the context. But in case of skills, it is only loaded at runtime. So what is only loaded is like the name and the description. So this is very less number of tokens which the agent needs. But whenever the agent thinks that okay, this is a task for which I need this skill, it will try to hot reload this entire context into its memory and then try to like get information. So basically, like in this case, what I'm showing you is like design to code skill, which basically like lists the different process which you need to follow to make like a design to code vision to happen. Like this is like a way, like even if like you as a designer want to like write a skill, you can easily write in a text format. But there are some standards around that. I think like I would suggest you guys to go to agentskills.io. That is the place where they have given very good documentation of like how to write skills. So in this case, like we're encoding like the entire like workflow from inspection to building to verification to then publishing. So it's kind of like also like the good properties, like these skills are reusables. Like you don't have to write it again and again for like Gemini or like Codex or any kind of different CLI. And the good thing is also that like you can capture the behavior of how as a human you want the agent to behave into this one text file, or sorry, this one markdown file, I should say. Okay, should go to the next slide. And this is another very important concept which we have to follow when we are building this long running agents. Uh, the reason why this is important, like the sub agents, is because any multi-agent design, like I think, like especially when you're having like long running sessions, uh, it's very important to maintain like how you maintain the context. Like some kind of like context is like a working memory for agent, and currently the agents are not very good when they have a very long context. So there are like some benchmarks like needed in the haystack, context rot, these terms you might have listened about. So we need to always make sure that we manage the context pollution and try to like not make it like put everything into like one context, right? Because if the agent is running for a long time, it will just keep on using that to append that to the context. So sub agents is a concept which is used while building these agents, where you specify specialized agents which have their own working memory, and they communicate with this orchestrator agent or main agent which I told you in the beginning. uh, so in this case, for example, like we are building like this design parser agent, which I think is the job of this agent is to parse the design to give some information of how should we plan to solve this design to code, how should we think about this design. So that's the job of this agent. It communicates that design flow either in the form of file system. It can store its output in the file system, which the main agent can then know about. So it has different ways to communicate with the main agent. And then there is this another agent called as like uh, like the code generator agent. So the job of this agent is it's a specialized agent trying to like just write good React code. So they're very specialized in their roles, and then the main agent can orchestrate between that. And so that helps the job of the main agent also, because now it doesn't has to remember everything. It offloads the job to these sub agents here. And as I mentioned before, like these sub agents also, you have to register that to the agent runner, so that the agent runner knows like which sub agents I can call. And the next thing is like hooks. So hooks are like a way to like basically like they're like operational control points. So basically like you can basically like they get invoked based upon any kind of events. So it's the concept is very if people are familiar with GitHub hooks, it's very similar to that. So you can basically like define like event boundaries, like you want to call this hook event before compaction. By compaction I mean like, because all these like Claude Code or Codex and Gemini CLI, they have some context limit. If they hit the context limit, then they compact the context. So if you want to invoke something before that event, you can do that. So you can also invoke an event before a tool call, before any sub agent outputs completion, etc. So you have different ways to do that. And then you can use it for like basically like observing things, like as I mentioned before, for evaluation, for tracking, to understand like, okay, if your tool is behaving in the right way, what kind of outputs you're getting across different steps, because this is not a single step, right? You also want to make sure that your system is reliable, like you can observe it. So in this case, what I'm showing you is like example of like of two hooks. One hook is basically like being used before compaction, like before the context is getting compacted, you try to like run this hook to preserve whatever knowledge the agent has done. And then there is another hook which is called as like preview guard hook. uh, the job of this hook is to tell the coding agent, I showed you the code generator agent, the code generator sub agent here, right? Like, so when the code generator sub agent like finishes a job, like it wrote some front end code, like some web apps portion, you want to make sure that it's working correctly, right? So that hook can be triggered to give information back to the agent, okay, like this doesn't look like it's working, right? So these kind of signals are very important. Okay. Next I'll show you guys like so these are the, just to end the things there, I think like these are some of the big components which I think are needed. I think like there are a lot of concepts around like remote MCP servers, because like skills are something which are local file system based, but like if you're building in like some kind of like security based system where you need to make sure that the client requests are authenticated, you also need to think about remote MCP servers, things like that. But in general, for any kind of long running agent, you need to make sure that your agent can be sandboxed into cloud, and you can like use these concepts to make an agentic system work end to end. And obviously like you need to do like evaluation, which I think is a different topic and a very big topic in itself. uh, okay, lastly I'll just like try to show you some demos to just give you a feel of like how the input looks like and how does the output which you get from this agent once you fully build it, like how can it look like. Obviously things can be better with a better harness. Let me try to open it one by one. Like I don't have a way to show everything in one go. So this is, for example, like, okay, one second. So this is the example of this like Figma community page of a car rental website. Like I think like if you open in Figma, it will show you the same kind of like Figma files. So this is the input which actually goes to the agent, and then I think like let me show you the corresponding output. So this is the output which the agent generated. Like I think if you see, like it is the app which has all the different like layers. Like these are the images which the Figma file had. It basically like had all those endpoints being checked, it like uh different ways to filter it out. So it's not a full-fledged app, but it's immense. If you see like from that big file, like it came to this app which is like functional in some sense. Like I think this that is like obviously like if you see like there are some endpoints which are not working. Like if I click this, they don't work, but like it really is like amazing to see like how it can build this thing. Then another example is sorry, let me show. So this is another website about a travel website landing page, and again this is the same thing, but you can see the corresponding output like here. Yeah, so this is the corresponding output for this. So this is like again like a page where you have like multiple endpoints, right? Like you want to go. So this is entirely created by the agent, like within like 30 minutes by reading that file, where it learned how to place the things in the right way, right organization. Like for example, like the landing page, like put this image in the right place, put the right endpoint, etc. And then lastly, I'll show you one more example, and then we can maybe move on to the next speaker. So this is a web page developed by the agent of a e-commerce like like a website, different tabs here. If you see like this one, it didn't create like endpoints correctly, but I think like it basically like created all like bars, things like that. And yeah, I think and then I think like lastly there is this another output which I think is about like a SaaS landing page. So basically like all these outputs, what I'm trying to say is like it takes sometimes like days to weeks for people to build right now, which the systems can give you like a good prior information. And obviously it's not the perfect output, but I think it is a very good starting point from where the developers and engineers can take over from. And like even the design community, like the people who only were able to were constrained to just use Figma, now they can easily see like okay how it translates into like a web app or a mobile app. Okay, I'll just stop here and then maybe I'll hand it over to the next speaker. Thank you.
Okay, thank you, Ishan. Thank you, Akriti. I'm Krishna. We have heard about what A2A is about or what MCP protocol is about, and Ishan has demoed us how this entire AI applies to a UI development part, and he kind of demoed us about the car rental part and e-commerce. So my expertise at Google is more on AI into supply chain and network allocation part. So I'm going to pick few case studies where we have used Gemini in terms to integrate with the real world supply chain systems. Let me present from here. Perfect. So I'm going to pick one integration to start off with, one case study, that is Gemini with Shopify app. So since we saw a demo about car rental, I'm going to take a similar example saying that, let's say there's a user who is looking for a particular sedan, and our UI or our particular LLM has to comprehend that information and now has to do a supply chain lookup. So in this case, right now LLM has only a static data. Maybe it has a little bit of information about the inventory like months old, and it does not have any real-time information. So in order to power up our e-commerce website, we also need a better system for our LLM to get the real-time information. And that's where the MCP protocol that we have introduced, the A2A communication that we have established helps us in establishing that system. So in here, I'm just picking an example saying that there's a user who has 10 products in their wish list. That's a more relatable use case right now given our context. So, and in this 10 products, let's say Gemini is now talking to Shopify MCP protocol part, saying that, how many products do you have available in this particular window? So we can see Shopify has its own dedicated MCP server, which lets us connect to it. And also Gemini can translate the user query and tries to call the Shopify API calls appropriately. Here is a technical architecture at a very high level, what we would be able to do with this. And in fact, what Shopify is doing right now at real time is it has its own MCP host server where it translates the query and then calls the appropriate data check, saying that in this case, is it inventory or is it in, other data checkups that it does. So in our use case, LLM calls the MCP servers, it understands the ask, it goes to the respective Shopify data check and then gets back a reply. And it doesn't just give the reply, it also tries to compare it with the user wish list. Out of 10 products, let's say based on the response I got from Shopify, only 8 are available for you to make a place an order right now. 2, you might have to wait for a certain time. So that sort of response formatting is also what LLM does here. This is the same example we have here. You can see a code snippet on how we can configure the MCP part of Shopify, on how we can plug it in our code base there. And also we have this MCP tool of Gemini function that calls the appropriate item availability check. And the prompt engineering part we already spoke about earlier. It's the user request. But also like Ishan mentioned about the skills, here the agent is also having a set of instructions, saying that this agent is only particular to talk about the inventory lookup. And that's how we limit that agent's context and scope. And in case of scenario 2, we are still sticking to the Shopify supply chain part, where here we are trying to say, now I have already placed an order. And I haven't even received it yet. And I just asked Gemini, can you go check it up? And what happens behind the scenes is Gemini now understands the user query and tries to connect with Shopify part. Now, earlier agent was inventory agent. Now the second agent here is going to be a order checkup agent. And as Ishan mentioned, we have sub agents here. So if Shopify is the main agent, we have multiple sub agents in it, where it orchestrates saying that, okay, in this case, let me go and call search order agent and fetch the information part. So that's the tools. And the next part is the intelligence, where Gemini comprehends, saying that out of 3 orders that John has placed, 2 were delayed due to the northeast weather issue that we have, the winter storm earlier. And how does Gemini get this information is, here it also connects with Gemini weather report. So that it's not just now talking to Shopify agent, it is also connecting to the internal Google weather app too. So that's where we see that one LLM or one particular interface is now connecting with multiple agents with limited context and trying to comprehend everything and put together a story for the user at the end. And this entire thing is binded by the A2A and MCP here. I was just calling out the A2A implementation a lot right now. And as Akriti mentioned that we have a JSON structure, right? Now for an agent, when it gets published, it needs to have a particular agent card. Internally, we limit saying the instructions or a skill saying that you are expertise in this. But externally, each and every agent has to have an agent card, a JSON structure that tells the entire world that this particular agent can fulfill this particular request. So that's the discovery part of an A2A implementation when we dive into the case study, what we have learned. And the other thing is atomic handshakes happens between the agents. That is, it's not just a stateless, it's going to be a state preserved. When an agent talks to its sub-agent or to an external agent, it needs to have a context retained at the end to, frame, to have the conversation there. And also the agent does not just gives us a response back, it asks a clarifying question. In the Shopify example, if you see, John has 3 orders. But what if I haven't even given you the John's credentials or the the order related zip code or the order ID to the Shopify agent? Now, I wouldn't want the agent to abruptly end my conversation then and there. I would expect a clarifying question saying that, can you provide me with the order number? So what we learned about this A2A integration is we have these atomic handshakes where the context is preserved as limited as it adds value. And we have this clarification artifact that is a back and forth churn. And the third part is the permission delegation. We also have, since we're talking about A2A handshake, it's quite expected that we use an authorization, a security policy there. And here we notice it's an OAuth scoping part. I'm going to go to the next slide here. So we have seen about the Shopify integration, and then we have another case study where Gemini at a very, I think last month, it has also announced that it is integrating with SAP Joule. That's an agent that SAP has launched. So now we are not just talking about a e-commerce website. Now we are talking about a huge landscape, enterprise level supply chain where we are integrating with an SAP system too. What happens here is similar to what we have heard, the discovery of agent cards. We have this agent handshake between Gemini and SAP. Gemini has this agent ADK toolkit where it orchestrates all sort of agents. It hosts the agent and it connects with the remote agent as needed. So let's say in my example that I have found, there is a user that has been not awarded a particular percentage of promo code. He has been charged full amount, but he has a promo code that hasn't been applied and he would like to have a refund. In this case, we have this Gemini talking to SAP to share the promo code and also to ensure he gets the refund. Now, when you look at, let me take to the next screen, maybe it has more information there. Okay, so as you can see here, we have a cross-app delegation. Firstly, the Gemini agent looks up the Google Drive, ensures it has relevant access permissions for the user details, for the user information, and then fetches the discount code, whatever that amount is. And then now it connects with the cross-app delegation, that's the SAP agent, gets the payment acknowledged, and then updates it back to the email thread. So that's pretty much what the financial dispute case study that we have seen. There were certain learnings that we have noticed when we're looking at this e-commerce integration for each and every agent. This is what we have noticed. One is the broken telephone effort, saying that, like Ishan mentioned, there's a token limit on how much an LLM can process at a given limit. In the same way, when we are having agent-to-agent communication, not just sub-agents, but also the external agents, we have huge amount of data being written, and the LLM loses its attention over, after, I think Gemini has 1 million tokens per day as a valid one. And when it has more than that data written, LLM loses its attention. So that's the first one. So we also have to ensure our agent returns a meaningful chunk of data for an LLM to process. So that's first takeaway that people miss. The other part is race conditions. In a supply chain world, it's important to understand that the data we fetch through the agent also has time to live. And that particular part has to be updated into each and every JSON packet that we receive. Similar to what we have seen earlier, like depth one, so that it doesn't go to multiple frames of information. Here in supply chain world, if I have to translate that, it is pretty much as TTL, time to live. And the third one is observability, which we haven't mentioned in the slide deck, but what we have noticed is it's about the logs. Unlike the traditional logging system, we also need to opt for a distributed tracing to ensure that these A2A issues have been, addressed appropriately. I think there's an open telemetry tool, if I'm not wrong, that helps us to debug into A2A issues in long run. So that's pretty much what I had for case studies. I'm not sure if we have any dialogue for open questions or so.
Things. Okay. So I don't think there are any questions, but thank you very much for presenting. It was very interesting learning about A2As and MCPs, how they connect everything. And thank you.
Thanks for having us.
Thank you.
Welcome.
Thanks.
Thank you for listening to today's guest speaker. We will be having more guest speakers tomorrow at March 1st, 2 p.m. EST.